mind. All right, okay, thanks very much, Aline. Thanks for the invitation and the introduction. So as Aline said, I'm Animesh from the University of Warwick, and this work that I will talk about, which is very much in preparation at the moment, is mainly done by Andrew Jackson, who is a PhD student in our group, funded by the Quantum Computing Hub, and also in collaboration with Theodoros, who was a postdoc in our group and is now a LabourHume research fellow. So what I will share and talk about is done primarily by these people. Right, so as the title says, this is a talk about estimating partition functions. I do not need, I hope, to spend too much time on why we care about partition functions, but I will still give you sort of just to make sure that we are on the same page, the sort of textbook motivations for why we care about partition functions. Well, the partition function tells us everything that there is to know about equilibrium thermodynamic properties. And these typically come through sort of, you take the log and the derivatives with respect to various things. So that is why it's important. We also know that it's important in particular in understanding things like phase transitions and so on. And these go back to these old results by Li and Yang about the zeros of the partition function, sort of marking out where the complex zeros of the partition function, marking out where phase transitions are, and so on and so forth. And I will come back at the very end to mention what is probably happening in this kind of topic in the field of quantum computation very briefly. But this talk is about a classical algorithm for doing these things. I guess the one point to understand here or keep in mind is that when we estimate the partition function, we will typically talk about, or actually almost entirely in my talk, I will talk about relative error. And that is because if we can estimate the partition function to a small relative error, then when we take the log, it becomes a small additive error or a small absolute error. And then that's how we get all the quantities we are interested in up to some small absolute error. Right, so, okay, so what is the partition function? Well, I mean, we all know how it starts. We're given a system of some particles with a Hamiltonian and some temperature. Sorry, is there some question at the corner? Did I see someone typing something? Okay, sorry, it's Ali saying to answer question answer. Sorry, I got distracted. But anyway, so we're talking about a system of n particles with a Hamiltonian and some temperature. And I guess the first question, of course, is, well, what temperature are we, or what system are we talking about? So there's sort of a whole set of possibilities. I tried to sort of separate them up into sort of 4 categories, let's say, sort of typically talking about whether the physics is quantum or classical, whether it's a continuous or discrete. And what I will talk about today is entirely in the bottom right corner, which is a quantum discrete system. And for that, we will consider the canonical partition function, which is the trace of the exponential minus beta h operator. We can also talk about the grand canonical, but that doesn't make a big difference to what we are talking about. Whether what I'm saying today applies to any of these other boxes is something that is yet to be determined. They may be applicable, they may not be applicable. I do not yet know, but this is probably a good thing for the discussion session to hear what people think about these things. But I will focus, as I said, on the bottom right corner for the talk today. Right, so what do we mean precisely? Well, okay, so this, I guess many of you are familiar with. So the typical system is, well, I have n electrons, I mean, it could be fermions, and then n sort of other species, typically more massive in some 3D system. And this I'm sort of pointing out as a concrete example. It doesn't have to be this problem. But what we typically do when we have a problem of strongly correlated fermions or strongly correlated electrons is we ignore the ion dynamics, which are much more massive. And then we choose some orbitals and we choose some unit cells, and then we write a Hamiltonian in the sort of spin operator basis. So we have the hopping terms, we have the site energies, we have the interactions, and then we have longer range interactions and so on and so forth. And very often at some point we set the higher and higher order interactions to 0. And the typical example that maybe people in the condensed matter community are quite familiar with, which is the single band Hubbard model, where we talk only of the hopping terms and typically the on-site sort of interactions between the spins and so on. Again, what I will say is not unique to this particular model, but I thought I would give sort of this as a motivation and something concrete for people to think about as I go through the talk. Now, but the Hubbard model in particular, obviously, is not meant to give an accurate quantitative description of a physical system of solids with interacting electrons, but it is expected or believed, let's say, to capture some essential features of such systems. And the prominent one is, of course, high temperature superconductivity, in the context of which the Hubbard model is very frequently studied. And sort of digging into this a bit more, I guess many of you are probably familiar with the argument that the Hubbard model may someday help us understand what high temperature superconductivity, where high temperature superconductivity comes from, or sort of some sort of predictive power of these things. And I mean, I just picked two sort of examples. So you see this sort of review from now almost 10 years ago by Scalapino saying, well, we've learned so much based on Hubbard-like models, and then some very recent paper by the Simons collaboration, sort of saying, well, if you actually look in the regime of large on-site interaction, there is no superconductivity. It turns out there is superconductivity in these models if you look for sort of weak on-site interaction. But there are sort of all kinds of debates as to the predictions of the model, whether the model itself is a meaningful sort of surrogate for the physics of a given problem is not something I'm addressing. The aspect I'm addressing is that if I pick one of these models, such as the Hubbard model, well, how do we compute things? And so that's where a lot of the debate is about. And that is where computing things like the partition function make their entry. So if I did want to compute the partition function, I guess everybody knows this, but I just want to make it clear so that primarily so that the notation is in place. Well, the obvious thing you could do is analytically, you could just diagonalize your Hamiltonians. If I have my Hamiltonian H with some eigenvalues lambda I, then of course the partition function is well, the exponential of just the eigenvalues added up. Now, if my Hamiltonian is on some lattice lambda, and I will use the symbol capital lambda for the lattice all the way through, and the mod of lambda is just the size of the lattice. So if I have sort of a 4 by 4 lattice, then mod of lambda will be 16. The dimension of the Hilbert space is exponential in the size of the lattice. Nevertheless, actually for the Hubbard model, and I was surprised to find this a few weeks ago, somebody has managed to analytically diagonalize the 4-site Hubbard model, and that's a very useful case to start with. So a 4-site Hubbard model has 2 to the 2 times 4. So it's a 256 by 256 Hamiltonian, so just 256 eigenvalues. And that using the symmetries and so on can, as it turns out, be diagonalized analytically. But in general, of course, these kinds of problems are not amenable to analytical diagonalization, even if you include all the symmetries and so on. And so we are left with numerical techniques. And here, of course, there is the standard trade-off between time and space. So either you need very large memories because we're talking about sort of exponentially large number of eigenvalues or Hilbert space sizes, versus if we want to do it sort of statistically, then it's a question of time question. So just to sort of give, I guess people are probably already familiar with these things, but just to sort of make it absolutely concrete, what we are talking about, if we have a 2 by 2 lattice, if I just count the number of elements in my Hamiltonian, very sort of generic fraction of an MB. If I go to a 2 by 2 cube, now I'm getting to GB scale memory, probably fairly standard these days. But now if I go to 3 by 3 square lattice of the Hubbard Hamiltonian, now you see we are getting to fractions of terabytes, and by 4 by 4, it's really becoming astronomical now. So the space constraint on the memory actually kicks in very, very swiftly. The standard sort of workaround for this is therefore to use approximate methods, and in particular sort of Monte Carlo type, quantum Monte Carlo type things. And here, of course, the standard problem is again a different kind of problem, which is the sign problem. So if I sort of decompose my exponential in a power series and then do the trace of each term, what I find is that I have to then sum over things which may be positive, negative, or zero, and that then requires a larger number of samples, and that's sort of the sign problem, obviously. So what can we do about this? Well, the sign problem, well, there are many ways of fixing the sign problem approximately, and this is just a recent review that sort of tries to collect all the methods. As you will know, there are probably in the audience people who are experts on some or all of these methods. And each of these methods can, in some class of problems, sort of get rid of the sign problem. And then they work sometimes very well, and then they stop working when they don't work. And then a lot of people spend a lot of time trying to understand, well, when does it work? How does it work? When does it not work? Why does it not work? And all kinds of stuff. And that's all very interesting and useful. And that's really the physics approach to the sign problem. Or I guess to any problem really, which is to find ways around it. I guess what we have learned in theoretical physics may be coming from the quantum, sort of spurred by the quantum computing aspect of things, is the computer science approach. And what the computer science sort of says is that, yeah, you may have all kinds of techniques of easing the sign problem, but in general, you cannot do it. And so this is just a recent paper from last year, which says, easing the sign problem is generally an NP-complete problem for nearest neighbor Hamiltonian. So you may be able to do it for certain sizes of problems, certain class of problems, but in general, it's going to be very, very hard. So NP-complete is something I will not get into. It's one of these complexity classes that is believed to be hard or very, very hard, let's say. So there is unlikely to, I mean, it doesn't prove that it is impossible, because it's always possible that someday we will find that NP is within P, which is the polynomially sized complexity class, but it is believed to be unlikely that as we stand. So in some sense, you might ask, well, where do we go from here? Do we have any other way of dealing with these kinds of issues? So that's what we'll talk about. So let's go back to sort of the elementary basic things that we know about. So let's just take the simplest non-trivial case, a 2 by 2 Hamiltonian. I can always write it as this kind of matrix where the H are real numbers, and then I can rewrite it as a sum of 4 terms where I is the identity, 2 by 2 identity, and X, Y, Z are the Pauli matrices. So X is sort of so Z is 1 and minus 1 on the diagonal, Y is I and minus I on the off diagonal, and X is 1 on the off diagonals. So in terms of those operators, I can then try and ask, well, what is my sort of this exponential operator going to look like? Now, of course, you all know that X and Y do not commute with each other, and Y and Z do not commute with each other. So I have to deal with the first problem, which is when I exponentiate this operator, I have non-commuting things. So we do what I guess you all are familiar with, which is the Trotter expansion. So that's this sort of bold T here. And I just do the simplest sort of first order Trotter expansion, which is I sort of decompose my exponential of this kind of operator as a product of the exponential of each of these on small steps of size 1 over capital R, and then I raise the whole thing to capital R. I mean, you can do better higher order things, higher order Trotter Suzuki expansions, but it suffices for us to just look at the first order just to get an idea of what we are talking about. So this will be obviously one source of error because there is some approximation, but again, as R gets larger and larger, we know that we can make this error smaller and smaller. So this is well understood. So now I can trace both sides of this. The left-hand side is just the partition function that I wanted. The right-hand side is something we hope is close to the partition function, not exactly equal to it. So that's the trace of the trotterized operator, let's say. Now, as I said, so there'll be some error, and the error is given by the operator error. If you want to look at each trotter step, I'll not go into the details of this, but this can be computed for any given Hamiltonian, and we just call it the trotter error, epsilon trotter, right? So that's the one of the quantities that we have to keep track of in terms of the error. And then Z prime is the estimate that we have for Z, which is within this relative error. Of course, we want epsilon trotter to be as small. Well, we want it to be small. And of course, our computation will get more and more expensive as we make this smaller and smaller. But what about the actual trace of this? Well, each of these terms, as you realize, is of the exponential of some real number times one of the Pauli operators. Because the Pauli operators all square to the identity, and the identity, of course, also square to the identity, I can do a series expansion, a power series expansion of the exponential, and because all the squares will become the identity, I can write this fairly familiar sort of identity where I have cosine hyperbolics and sine hyperbolics, and we've put the sign of the sort of the coefficient Rj. If you remember, the Rj are related to the coefficients of the Hamiltonian Hj. So sine of Rj is basically sine of Hj with the Paulis. So that's one identity. The second identity, of course, is that the Paulis, what is mathematically known as, form a group. So the product of any two Paulis is the third Pauli, often with the plus or minus I sign. So this kind of product raised to some R power is going to be, in the end, a sum of 4 terms, at most 4 terms, with identity X, Y, or Z, and some complicated functions F, which is basically the product of the sine and the cosine hyperbolics. So if I want to now take the trace of this quantity, well, I know that the trace of the Pauli matrices is 0. So only the terms that multiply to the identity will survive. And that's my estimate of the partition function. That's Z prime, basically. So you see, and this is sort of in some sense the crux of what we are talking about, which is that we are not doing explicit matrix multiplication here. We are using the properties of the Pauli matrices to get to an estimate of the partition function. And this, in some sense, is sort of our algorithm, if you want to call it that way, our classical algorithm. Now, what do we do more generally? Well, more generally, we will, as I have said, have n electrons on some lattice. Of course, to go from electrons to, because electrons are indistinguishable, I need to go to some distinguishable sort of particles, which typically called qubits in the quantum computing language. And as you know, there will be some sort of overhead in this. So typically, people may be familiar with things like the Jordan-Wigner transform and so on, which actually scale with the number or with the size of the problem. But in quantum computation, in the last few years, there have been a lot of study on minimizing these numbers. And now you can get what are called low weight encodings. And low weight can typically be, the best known are typically between 3 and 5, for instance. So in this paper, and there are many, many others studying these kinds of problems. You basically end up with a Hermitian matrix, which is obviously exponential in the size of the lattice, maybe with some constant overhead. But because it's in the exponential, these little numbers make big differences. But anyway, whatever that Hilbert space size is, a Hamiltonian on that Hilbert space can be written as a sum of a certain number of terms of tensor products of Pauli operators, because just like in the 2 by 2 case, Hermitian operators or Pauli matrices are a basis for Hermitian operators. So any Hermitian operator can be written in this form. And then we do the same thing as we did last time, which is we do a Trotter expansion, and we get exponentials of these Paulis, which then go into sort of identities and Paulis using the properties of the Pauli matrices. And then we take the trace, where either they will all become zero, all the ones that are not all identities, and the one that is all identity will have the dimension of the Hilbert space as its trace. So that's basically our algorithm in some sense. I mean, that is our algorithm, to be clear. So how does this actually work in practice? So just to get an idea of how many terms we are talking about, well, the number of terms will definitely depend on the lattice we have. It will also depend on the kind of interactions we allow. And this is where you go back to the physics of what you are trying to understand and so on. I mean, for instance, if you do nearest neighbor on a square lattice, you will have 4 times the number of lattice sites with periodic boundary conditions. If it's a cubic lattice, you will have 6 times. If it's next nearest neighbor, you will have 8 times, and so on and so forth. But anyway, you will have a certain number of terms in this sum, and therefore in the Trotter expansion. And the number typically will be some number L, which will be less than or equal to the number of terms. That is because some of these terms will actually commute with each other, right? So for instance, X and Z do not commute with each other, but X tensor X commutes with Z tensor Z. And so this is another area where we have been benefiting a lot from recent efforts on the quantum computing side, where people have spent a lot of time and effort trying to really nail down the last factor of fraction of a half or things like that, to sort of minimize the number of gates and qubits one needs to do a quantum simulation. But we can benefit from that here as well to sort of make our Hamiltonians as compact as possible. So once we've done that, well, we will have a certain number of Trotter terms we will need. And this, as I said, will obviously increase as my Trotter error decreases. So of course, if I want Trotter error of 0, I need an infinite number of terms. We will not do that in practice, but whatever small Trotter error we choose will determine how many terms I need. But more importantly, it will depend linearly on the number of terms in the Hamiltonian. So let me remind you again, the number of terms L will be less than, in the worst case, will scale with the size of the system. So in total, and the zeta, the xi squared is just some energy scale from the Hamiltonian. So if you look at this entire Trotter expansion or approximation rather, you see there are L times R terms in the whole sort of expansion, right? Because each one has L and then I repeat it R times. So LR, from here, you see has order L squared terms, right? So it also depends on the temperature and so on and so forth. So obviously, the smaller the temperature, the larger beta and more terms you need, and all these are expected. But what we are really interested in is in the scaling of the size of the problem. The size of the problem is in L. So we need to basically do a multiplication of these matrices over order L squared terms, right? So how do we do that? So this is now the second sort of aspect in our algorithm. We need to track these L squared matrix products without explicit multiplication. And that's the whole point, because if we have to do explicit multiplication, then I have huge matrices and I'm back to my sort of memory problem. So we know already this identity, that the exponential of some Paulis can be written as identity and Paulis. I can now redefine some of these quantities, multiply with some positive number, divide by some positive number. And what I have is, actually, maybe if we go back, what you realize is that cosine this and the sine of the absolute value, these are positive numbers. So basically, I can divide by their sum, which happens to be exponential of mod r, and make them into probabilities. And then what I have, my approximate partition function, is the trace of this operator's Ej, let's call them, and there are L of them, all raised to the power r, which is a probabilistic sum of either the identity or some Pauli operator with some probability Pj. Right? So this is, as I said, the next step of our algorithm, where we now have this quantity z prime tilde, where we sample this product by randomly picking identity and Pauli a certain number of times, and I will tell you how many times and so on and so forth. So this is the second sort of error, or the other source of error in our algorithm that we have to keep track of, and this is the sampling error. But this can be done, you realize, precisely because we are talking about thermodynamics and the partition function. If we were looking at time dynamics, these quantities would not be hyperbolic sines and cosines, but normal circular or polar sines and cosines, and then they will not be positive and probabilities anymore, and therefore this argument will not work. Right? So this is specific for the time dynamic or for the thermodynamics. And for time dynamics, this thing is still exponentially hard, and therefore you probably need a proper quantum computer anyway to solve that problem. But for this particular problem, for the thermodynamics, we can do it classically, as we are saying, right? So what is the sort of the sampling error as well? So let's say, well, so we have Z, which was the original thing we wanted, Z prime tilde, which is the final thing we have. We do standard triangle inequality. So the first term is the Trotter error. The second term is the sampling error. I'm not going to go into a full sort of error analysis of the algorithm. But what you, I hope, can see is that there is some large constant factors. If you go back to the previous slide, this depends on the parameters of the problem, but it's a large, basically it's a number. So we can call that some large constant C. It will also have the normalization of the Hamiltonian and so on in it. So I can rescale all my quantities by this large quantity, large constant C. And I have the sort of small z prime tilde, which is now the trace of all these quantities. And I can go back up here and divide both sides by this large constant C, and then I will end up with an estimate of this quantity z with z prime tilde, which is less than some relative error, which we set. And how many samples do I need to get some total error? Well, I have the Trotter error part, which is the LR part, right? Because I need to repeat this L times R times. And then each sampling error will have some error given by E sample and then the value Z on the right-hand side, right? Just from this term, the second term from the sampling part. And I can put it all together in terms of all the original things I had. So as I said, you will have sort of the runtime or complexity of the algorithm. If you were sort of talking in computer science language, would say, well, it goes as L squared, which is the number of terms in my Hamiltonian, some dependence on the temperature, some energy scales in the Hamiltonian, 1 over the log of 1 plus the Trotter error. I mean, if the Trotter error is tiny, this is just E Trotter, basically, because log of 1 plus x is x. And then I have E sample squared, and then C squared over Z squared, where C is the sort of the normalization, and Z is the actual partition function. And this, now you realize, is that if the partition function Z is large compared to C, or it's comparable to C in the sense that it has its exponential scalings in itself, they will cancel out, and there will not, the algorithm as a whole will scale like L squared with some constant factors depending on the physics. If on the other hand, the partition function of the system is small, then this C squared will dominate, and then you will have things like things like L in the exponential and so on, and then the whole thing will sort of blow up horribly as exponentials, squares of exponentials and so on. But this, you realize, is going to be the case for any algorithm that does relative error approximations. You will have things like of the form C squared over Z squared, and if Z is much, much smaller than C, then things will scale exponentially. So that's not unique to our algorithm. This is just the nature of the problem. So I just wanted to, because I had promised some numerical results, but as I was telling Aline before we started, we have been somewhat slow in running these things. on our machines here at Warwick. But what Andrew has done is sort of taken this algorithm and applied it to sort of just the 2x2 Hamiltonians, just to see that it actually does, or it's not obviously wrong, let's say, for a start. So he sort of set some relative error bound, which said 0.1, and then he generated about 100 Hamiltonians, 2x2 Hamiltonians, picks a bunch of random temperatures, and just computes the partition function using our algorithm. Because it's a 2x2 problem, he can also compute the partition function exactly by diagonalizing the whole thing, and then he looks at the relative error between the exact diagonalization and our algorithm, and as he shows, they're all within the error bound. So the algorithm does what it promises, which is given an error bound, it gives you a partition function that is within that error bound. And the green line denotes the average, which is not particularly meaningful in this case because he's picked random Hamiltonians and they don't really have any physical meaning in that sense. We have then, and Andrew has then gone on to apply this to the Hubbard model. He's worked it out for the 2x2 lattice and it works. He can't notice any sort of discernible difference in the time between our algorithm and sort of just, again, full diagonalization of the 256 dimensional matrix. So that doesn't really tell us anything. What we really then want to know is, well, how does this perform on larger lattices, 3x3, 4x4? And we are in particular comparing with sort of full diagonalization of these Hamiltonians. There are libraries that can do that. I think sort of, from what I understand by talking to people who are experts in these sort of 3x3, 4x4 is sort of the edge of what people can do. 5x5 is certainly not something people can do. And by 5x5, I mean the Hubbard, single band Hubbard model on a 5x5 square lattice is not something people have done. Full diagonalization off. So we are sort of hoping to see if our method can do those things or if it can do it. But I mean, I hope you realize what our algorithm tries to do is to shift the burden away from the space part, which is the memory, to the time part, which is sampling. So that's broadly the sort of this overarching strategy about this algorithm. Right, but you realize that, I mean, I've sort of said, well, this all works and fine, but I also said earlier that, well, the partition function of a typical problem is very, very hard because obviously the sign problem is hidden there somewhere. So where did it all go? So it seems sort of I've pulled a trick. And to understand that, we now need to go into the second part of the talk, which is the quantum inspiration for our algorithm. So we started by saying, well, we have a Hamiltonian, which is a linear sum of these tensors of Pauli's. It turns out that getting that form is actually computationally hard in general. Well, how hard? Something called DQC1 hard. So then we need to go into, well, what is DQC1? What does that even mean? So in fact, we need to go back 20 or more than 20, maybe almost 23, 24 years in the early days of quantum computation, where people were trying to understand what quantum computers can do. Bain and Laflamme, who I guess people who are from the quantum computing field will know the names, came up with this model of quantum computation, which they call the power of one bit or one qubit. It's also called DQC1, means deterministic quantum computation with one bit or one qubit. Back then, the word qubit had not sort of become predominant, so they still use bit. And it's called the one clean qubit model because of the following reason. I have one qubit, which is in the state 0, and then I have m other qubits, which are in the completely mixed state, right? So if I have a qubit in the completely mixed state, its density matrix is half times the identity. And then if I have m of those, I have the 2 to the m dimensional identity with the proper normalization. And then I implement this quantum circuit. So H is a Hadamard gate. It takes 0 to a superposition of 0 and 1. And this symbol, this dot with the line, means what's called a controlled unitary. If you're not familiar with quantum computation, it's not particularly important. What this circuit, as it's called, does, it gives you an estimate of the normalized trace of the unitary, right? You might say, well, why do we care? Or who cares for the normalized trace of the unitary? It turns out getting traces of unitaries is typically what quantum mechanics does, right? Because expectation values are traces of things. Partition function was a trace of something, not a unitary. In fact, if I had e to the minus ith, that would be a unitary. And so traces of unitaries is a fairly generic thing that shows up in quantum calculations. And one of the things they were able to show, or they were able to prove in their paper, and this is a theorem from their paper, is that the ability to efficiently estimate the coefficients of the Pauli operator expansion of the operator implemented by a quantum network is equal in power to DQC1, right? So when they say operator implemented by a quantum network, what they basically mean is a unitary gate, right? So this is before the language of quantum computation had become standardized. And what they're saying is that the ability to write a unitary operator as a linear combination of Pauli's and tensor products of Pauli's is what they call DQC1 hard. So it's what's called a hard problem for this complexity class, if you're familiar with quantum computer, if you're familiar with complexity theoretic sort of terminology. But what does it mean to be DQC1 hard? I mean, I just made something up, right? I defined a problem and I said, oh, it's hard for this computer. What does it mean? So to calibrate, it is believed, because as you may know, in theoretical computer science, things are really, really hard to prove. So there are a lot of conjectures based on other conjectures, based on other conjectures, based on things people believe are rare or unlikely and so on. What we know, or what we believe rather, we don't know for a fact, we know is, or we believe is that DQC1 is more powerful than a classical computer. So that's this oval P. It is also believed to be less powerful than a universal quantum computer, which is denoted by PQP, right? So for instance, if you've heard of things like factoring and so on and so forth, it is not expected that the DQC1 computer, the one with this kind of a circuit, will be able to do, for instance, factoring. But there are problems which a classical computer cannot solve or finds hard to solve, which the DQC1 can solve efficiently. And actually estimating the coefficients of this expansion is one of these problems, as it turns out, right? Now, that's sort of the computer science argument of why DQC1 is hard. As it turns out, many years ago, back when I used to be a PhD student, I had looked at this particular problem of what does it mean for this computation DQC1 to be hard. And what we had actually found, and this is, 2007, with Kiefer Vidal, who used to be in Australia in those days, was that we showed that you could not efficiently simulate a DQC1 computation with a matrix product type computation, right? So that's what we showed, that measured through the operator Schmidt rank, there is large amounts of operator Schmidt rank, and this shows the preclusion of efficient classical simulation of DQC1 by a whole class of algorithms, typically the matrix product state type algorithms. And the reason that is the case is, as you will know, those who are familiar with it, this matrix product type algorithms basically work by neglecting a whole bunch of Schmidt states or Schmidt operators or Schmidt ranks, the ones that are small compared to others. What happens in DQC1 is that they're all small. So in fact, you get sort of 2 to the n Schmidt values, all of which are of size 1 over 2 to the n typically. And this is what we prove also in this paper rigorously. And so you cannot neglect anything. And so you have to keep track of all of them. And then it becomes exponentially hard, because you have to now keep track of to the end states, basically. So the DQC1 is hard in a very tangible way. So going sort of deeper into sort of inspiration, about a year or so ago, there was this paper by the group from Los Alamos sort of talking about estimating partition functions in the one clean qubit model, which is where we had sort of started looking at how to improve this particular thing for a quantum computer. And then we realized, as Andrew and we were working through this, that it's actually getting the Pauli decomposition that's the hard part. Once you've had that, the rest is an easy classical step, and that's what we have sort of presented as the classical algorithm. So I hope you've gotten some idea of what the classical algorithm is and what the quantum background for it is, right? So we are not saying we have found a magical algorithm that solves hard problems. All we are saying is we realized where the hardness is and sort of exploit that fact. I just want to mention that obviously people within the quantum computation domain are trying to study these things on a quantum computer. So this is just a recent paper from, again, I guess people in the quantum computing world, we recognize names like Chris Monroe and so on, sort of trying to do thermodynamics on quantum computers with partition function zeros, based on this earlier paper from 2012, which I didn't know about, which is to find zeros of partition functions. And when they say a probe spin coupled to a bath, what they really mean is this particular circuit, a single spin coupled to a bath equally to all the particles. They don't make no mention of d equals 1. I guess they don't know it exists. Nor do the quantum computing people, who I thought ought to know that it exists, but anyway, they don't. So I think people are trying to do these things on a quantum computer, but that to me seems like sort of overkill. But I guess if you have a quantum computer, you want to throw everything at it for every possible problem that ever shows up. But anyway, so I think I will close now and conclude. So what have we sort of learned or gained? Well, I think what we have really, or what I have really understood is that the reason the partition function is hard, you may restate it as because of this decomposition problem instead of the sign problem, right? So, I mean, if you look at it one way, you will call it the sign problem and everybody knows about it. Looked at another way, and this is the bit we learned from quantum computation, you can equally call it, well, the partition function is hard because of the decomposition problem. And then, just as people have spent, I don't know, decades sort of finding ways of easing the sign problem, it is possible that there may be ways of easing the decomposition problem, and that may lead to a whole set of new algorithms and sort of better understanding of these things and so on and so forth. Right? In practice, of course, what we have is a classical algorithm if the Pauli decomposition is available, and that's the big question. So I want to sort of end with where I started. So if you have a some Hamiltonian of strongly interacting electrons, or typical strongly interacting many-body system, what we typically do, and this has nothing to do with any computation, just sort of the first level of abstraction, we go from this kind of sort of messy physics or chemistry problem to something sort of, I want to say, cleaner, in the sense that where we abstract away a lot of the physics of the ions and so on, and we pick orbitals, we pick unit cells, and then we have this operator C, in terms of which everything is defined. And what we really need is, given a lattice, given some encoding, some Pauli decomposition of these spin operators, right, for every sort of orbital and site and spin and so on. And once we have that, we can write out the whole Hamiltonian as a linear combination of tensors of Pauli, right? So although the general problem, given a Hamiltonian, it is hard to find the Pauli decomposition, as far as solving a given physics problem is concerned, my feeling is that we typically start with the Pauli decomposition. So the fact that sort of the general problem is hard as per computer science is true, but in some sense a non sequitur as far as computing these things are concerned. And so I hope that some of you at least will find this useful, if not interesting. Thank you.
Okay, thank you, Animesh. Now we'll have to take some questions.
Yeah, sure.
Unfortunately, I don't see everybody. So if you put the question in Q&A, when I try to activate your microphone so you can ask the question directly or raise your hand. And before anybody goes to ask question, so one thing, I will ask a question. One thing that you did in your Hamiltonian decomposition, you ignored all these higher order terms. These are mainly so you ignore some part of physics. My question is, what are the implications of keeping that terms in terms of the algorithm?
Well, so I guess you're talking about this here, right?
Yes. Yeah.
Yeah. So you can keep as many terms as you think is relevant for the physics you are interested in, or the chemistry you are interested in, right? What will happen is, once we go to the lattice picture, this will sort of lead to next nearest neighbor terms and next to next nearest neighbor terms and so on and so forth. And that will sort of, as we see here, lead to, let's see where, right? So these kinds of terms, right? So if you have nearest neighbor terms, you will have 4 times the size of the lattice. If you have next nearest neighbor, you will have 8 times the size of the lattice, and so on and so forth. So it will increase the number of terms, but it will not increase it exponentially unless you say, well, everything is interacting with everything, right? So, which is sort of, I don't know, from my experience, it rarely happens in a physics or a chemistry problem that everything interacts with everything with equal strength, right? So unless that happens, you will always have a polynomial number of terms. So what is now L squared, as I showed you here, will probably become L cubed and so on and so forth, but it will not become L to the L, which is what you will get if everything interacts with everything all the time with equal strength. So I hope that, so in our algorithm, we don't need to sort of cut away terms. You just keep as many as you like and go from there. I guess it was all very clear, completely useless or irrelevant. I don't know. Will I be able to see questions, or do you get to see questions?
You should be able to see them too. I see no question. I see some.
Okay, maybe I'm looking at the wrong place.
Oh, it's just a comment. Somebody. There is a question. Can this approach be extended to continuous systems?
Yes. So, well, the short answer is I don't know. The longer answer is we'll have to think about it. I think it may be extendable to, let me find that table, to quantum continuous systems, because even there we typically write, although we sort of define our Hamiltonians in terms of fields and so on, in the end, we do have to do a trace of operators, and maybe we can find some operator who's sort of, so as you realize, the technique that, or the trick that we are using is writing our Hamiltonian as a sum of operators which have a nice algebra, basically. So I think if we can do that in a continuous system, I think this can be made to work. But yeah, I really can't say anything more than that at the moment. But if people have ideas they want to explore in this direction, by all means, go ahead. Or if they want to discuss, I'm happy to discuss as well.
Okay, so if there are no more questions, we'll...
Okay, well, I guess. Yeah, I mean, if there are questions that people can think of at a later time, I'm happy to answer them by email.
So, so there is a question. Okay. Do you see the question? Do you want to read it?
So let's see. So I guess Andre Bruckner says, okay.
Yeah.
However, if the problem is so hard in terms of dimensionality and memory demand, why bother trying to solve it in light of quantum computing? Well, I mean, again, there are sort of two answers, right? So the first answer is sort of the mountaineering answer, which is well, because it's there. But I think, as I said, quantum a quantum computer it can certainly solve or sort of estimate the partition function, but it seems like it's an overkill because the DQC1 class is weaker than a quantum computer. So in that sense, it's it's sort of overkill. But I think the more important point is quantum computers of a size that can solve problems that classical computers cannot solve reliably do not yet exist. So in that sense, I think classical algorithms are still useful. And in my view, at least for the coming few years, more worthwhile, because they can probably help answer questions that quantum computers will not be able to answer for at least a few years, maybe more. So that would be my sort of view. I don't know if that actually answers the question.
Okay, Andres says thanks. Okay, I think there is no more. There are no more questions. We'll bring it to an end, I think.
As I said, I mean, if people have questions later on, I'm happy to respond by email.
Thank you, everyone, for participating. Let us hope we'll see you again at the next one. Okay, Viv commented.